This is Physical Chemistry, Part 4, Statistical Thermodynamics, Chapter 29, Probability, Section 29.1, Why Probability? In quantum chemistry, we study a very small number of atoms or molecules. In thermodynamics, we study a huge number of atoms or molecules, usually in the order of 10 to the power of 23. So from a few atoms to 1 trillion atoms, or from one molecule to 1 trillion molecules, we need a bridge to connect quantum chemistry with thermodynamics. The bridge is called Statistical Thermodynamics. Let me give you one example. Let's say we have 1 billion molecules. They occupy 2 different energy levels. And we can use quantum chemistry to compute these 2 energy levels and the corresponding probability. Assuming the probability of these molecules occupying the lower energy level is 90%. Higher energy level is 10%. And then we can simply calculate the average energy of this molecule. It's 0.9 times the energy of the lower level plus 0.1 times the energy of the higher level. Now let's generalize this analysis. Let's say we have n helium atoms. And let's calculate the internal energy of this n helium atoms. It's simply the sum of the energies of all helium atoms. And we have this equation. If we know that there are an infinite number of energy levels that the helium atoms may occupy, and that the probability of helium atom having energy epsilon j is p sub j, then we know this n, the total number of helium atoms, multiplied by the probability of a helium atom occupying the jth energy level, and this gives us the number of helium atoms that occupy this jth energy level with energy epsilon j. So again, this number of atoms have the same energy epsilon j. And therefore, the total energy of this n helium atoms, or you can say lowercase n mole helium atoms, is this. The total internal energy of all this n helium atoms is the sum of epsilon j times this uppercase n times p sub j. So this uppercase n times p sub j is the number of helium atoms with an energy of epsilon j. And again, just to make this more general, let's say there are an infinite number of energy levels. So we are summing over 1 to infinity. We can divide both sides by the number of moles, lowercase n. Again, this lowercase n is equal to the total number of helium atoms divided by the Avogadro constant. Now we have a new equation. The molar internal energy is simply the sum of epsilon j times the Avogadro constant times the probability of finding a helium atom occupying the jth energy level with a epsilon j energy. So again, this U divided by the number of moles, you get molar internal energy, and this N is the number of helium atoms divided by this number of moles of helium atoms, you get this Avogadro constant. We have learned this before. the probability of finding an atom or molecule occupying the jth energy level is proportional to E to the power of negative epsilon j over kBt. This is the so-called Boltzmann distribution, and that means if you have a higher energy level, there's a lower probability for an atom or molecule to occupy this level. And if your temperature is really low, that means you will have even lower probability of finding molecules occupying higher energy level. But when temperature is really high, and then you will see these atoms or molecules occupy all energy levels almost evenly when the temperature is really, really high. So this case of B is the Boltzmann constant. The value is 1.38065 times 10 to the power of negative 23 joule per Kelvin. And then we have this equation, the probability of finding a helium atom occupying the jth level is equal to this guy divided by this guy. So we know this P sub j, the probability is proportional to E to the power of negative epsilon j over kBt. So what is this sum about? Well, this is the normalization factor. By dividing this exponential function by the sum of all those exponential functions, we can ensure the sum of the probabilities is exactly 1 or 100%. We can verify this. We can sum up this. We sum up the probabilities, and we get this expression. Again, P sub j is this. So we're going to sum up all these terms from j equals 1 to j equals infinity. And when we do this, I want you to realize that this sum does not depend on j. Over here, j is a dummy variable, and that means you can replace j with I without changing the value of this sum. So that means we can take this sum out of the bigger sum. So we took it out, we put it in here, and we just need to sum up this exponential function and put it on top. And this number is equal to this number, because both the numerator and denominator are exactly the same. They are both the sum of the exponential function here. And again, if you feel confused, I would say you can replace this with I. This expression, this derivation, are still correct. And you can replace this with I as well, but you can replace with this with K, because in this derivation, I, J, K are dummy variables. So whatever you want to do. So maybe I should just keep this to be I. Alright, again, this sum is exactly the same as this sum. Now let's look at the molar internal energy. The expression is the Avogadro constant times the sum of epsilon j times pj. And then we replace pj with its expression here. And then, again, because this sum on the bottom does not really depend on j. You see j here, but j is a dummy variable. Let me give you a simple example. If you sum up the values of j, for j from 1 to 10, the result is going to be 55. It does not depend on j. So 55 is a number, it's a constant. It does not depend on the value of j. Also, if you sum the values of I with I from 1 to 10, as well. The sum is going to be 55. It does not depend on I. So really, the sum does not depend on this dummy variable. So that's why you can take it out here. And then you just need to sum up epsilon j times this exponential function. So pay attention here. In the numerator, you have this epsilon j. And in the denominator, you do not have that epsilon j. And if you look at this expression and compare this with quantum mechanical postulate 4, that can be used to calculate the expectation value of epsilon. This is a very good analogy. Now, epsilon j can be calculated from quantum mechanics. For example, if you have learned particle in the box, you know this energy level J is J squared times H squared over 8ma squared. If the particle is confined in a box with a dimension of A. So again, J is a dummy variable, and we can calculate the molar internal energy this way. We can simplify this expression by doing two things. First, we can set beta to be 1 over kBt. All right, so that will simplify this epsilon j over kBt to epsilon j times beta. And also, we can define a new variable, q. We'll call this q partition function. So we're just defining q to be the sum of this exponential functions. All right, and we can write q to be the sum of e to the power of negative beta epsilon j. And then we have a simplified expression here. This sum is replaced with q. On top, it's also slightly simplified. And by looking at this, we know this sum, the sum of epsilon j times e to the power of negative beta epsilon j, is equal to the molar internal energy times q over the Avogadro constant. So from here to here, it's just simple algebra. And we can further simplify the expression of the molar internal energy by evaluating dq over d beta. So we can evaluate dq over d beta. This is just the definition of q. Q is called partition function. So how do we evaluate this? Well, first, you want to know that the first derivative of a sum is the sum of the first derivative. So this is one of the calculus rules. Again, right now we're looking at the first derivative of the sum. And over here, it's the sum of the first derivative. So we can put an equal sign in between. And then we just need to evaluate the first derivative of e to the power of negative beta epsilon j with respect to beta. This is simple calculus, differential calculus. You just need to copy this negative epsilon j here, and then copy this exponential function here, and that's it. And by looking at this sum, this is the sum of negative epsilon j times e to the power of negative beta epsilon j. It looks awfully similar to this, right? So this and this are awfully similar to each other. The only difference is the negative sign. So I'm going to add this negative sign in here. So this sum is negative molar internal energy times the partition function over the Avogadro constant. So by looking at dq over d beta and this negative molar internal energy times q over Avogadro constant, we have this molar internal energy to be negative Avogadro constant times dq over q over d beta. dq over q is dlnq, all right? Because dlnq over dq is 1 over q. And therefore, dlnq is dq over q, right? So dlnq is dq over q. So really, the molar internal energy is equal to negative Avogadro constant times the first derivative of ln q with respect to beta. So now the problem is simplified to this. Somehow we need to get the expression of Q in terms of beta. And then we take the logarithm of Q. And then we take the first derivative of Ln(Q) with respect to beta. The result multiplied by negative Avogadro constant is going to be the molar internal energy of the system. So how do we get Q? Again, Q is this. What you need to do is you need to use quantum mechanics to compute, to derive this epsilon j. Again, the translational energy levels of a helium atom confined in a box of dimension A is J squared H squared over 8ma squared. So this is a classical particle in the box problem. So if you don't remember the energy expression or the derivation, I'd recommend you to review quantum chemistry, especially the one-dimensional particle in the box problem. All right. So what if you have a three-dimensional box? You have helium atoms moving around inside a three-dimensional box. Well, and then you just need to sum up the energy in the x, y, and z directions to get the energy level. And also, in that case, you need to take the degeneracy into account. For example, if you have helium atoms in a cubic box, all three dimensions are equal to each other. They're all A. And then if you have the quantum numbers 112 versus 121 versus 211, they actually have the same energy. They have the energy 1 squared plus 1 squared plus 2 squared times h squared over 8ma squared translational energy. All right, so you have a degeneracy of 3 in that case. So in that case, you need to take the degeneracy into account. That's why I slightly modify the equation. I put this G sub j here. If you have a degeneracy for this jth energy level, so G sub j is a integer. Section 29.2, Basic Probability Theory. Now we're talking about discrete versus continuous probability distribution. So first, discrete probability distribution, that means the number of possible events or outcomes is countable. So let me give you a few examples. If you threw a dice, there are 6 possible outcomes. So we have a number 6 here. If you draw a card from a deck of cards, there are 52 possible outcomes. If you threw 2 coins, 2 quarters, and then there will be 3 possible outcomes: 0 heads, 1 heads, or 2 heads. Well, but if you assume the 2 coins are distinguishable, especially if you label one coin A, the other coin B, and then you will have 4 possible outcomes. So coins A and B can be both heads, heads and tails, tails and heads, and then tails and tails. So in this case, it really depends on one thing. Are these 2 coins distinguishable or indistinguishable? Over here, if the 2 coins are indistinguishable, then you have 3 outcomes: 2 tails, 2 heads, and then 1 heads, 1 tails. Again, we do not care which coin is heads, which coin is tails over here. Now, if we flip n coins, and then how do we calculate the average number of heads? Well, there's a equation here, over here. You can just sum up the combination of selecting I heads out of a total number of n coins, and then you have 50% probability of getting a heads for one coin. Now you have I heads, so the probability of all these I heads or heads is 0.5 to the power of I. The probability of this n minus I tails is the probability of one coin getting tails, which is 1 minus 0.5. This 0.5 is the probability of getting heads. So 1.05 is the probability of getting tails. So you get this probability of getting tails for one coin to the power of n minus I coins. So again, over here, you are selecting I heads out of n coins. The remaining n minus I coins are tails. All right, so how do we get this number? This is the so-called combination. If we are choosing I coins out of n coins, the equation is n factorial over I factorial over n minus I factorial. All right, so what if the coins are rigged? What if you get 60% chance of getting heads and a 40% chance of getting tails? Well, then you need to replace this 0.5 with 0.6, and this 0.5 with 0.6, and then 1 minus 0.6 is equal to 0.4. That's the probability of you getting tails. All right, same equation. You just change the probability if the coins are rigged. Now let's talk about some continuous probability distributions. In this case, the number of possible events or outcomes is uncountable. So for example, the probability of finding an electron within a volume of space is uncountable. It's continuous. And also, the Gaussian distribution of errors is uncountable. A normalized Gaussian function adopts this form. It's a e to the power of negative x squared over 2 sigma squared times a constant. This constant is the normalization factor. By including this normalization factor, we can ensure the integral of this from negative infinity to positive infinity is exactly 100%. This is the shape of a typical Gaussian function. And over here in the middle, this is the average. And then sigma is the standard deviation. So within plus minus 1 standard deviation, there's a 68.26% probability. And then you can see between negative sigma and negative 2 sigma, there's a 13.59% probability. Beyond 3 sigma, there's only 0.135% probability. You can easily prove that this Gaussian distribution is normalized by evaluating this integral. So how do we evaluate this integral? We'll do variable substitution. We can define z to be x over the square root of 2 times sigma, and then x is square root of 2 times sigma times z. So you just replace every x with the square root of 2 times sigma times z over here, and you get this expression. And also, since z is proportional to x, if x is from negative infinity to positive infinity, then z is also from negative infinity to positive infinity. So what you do is you just evaluate this. And then you just take out all those constants, square root of 2, and, cancel the sigma, etc., etc. You get this expression. And this can be proven to be 1, to be the square root of pi. So this can be proven to be the square root of pi. What you need to do is you need to convert this to the square root of the integral of e to the power of negative x squared dx times the integral of e to the power of negative y squared dy. So you can do that because x, y, and z are dummy variables. And then you need to convert x and y to the polar coordinates in a two-dimensional space. So that means you need to convert x and y to r and theta. And then you can easily prove this integral is the square root of pi. And then you can finally prove that this Gaussian distribution is normalized. Again, let's look at this distribution here, and then you can make predictions about the probability of finding the value of x in a certain range. For example, between negative sigma to 0, it's 34%. Between negative sigma and positive sigma, it's 68%. And between negative infinity to negative 3 sigma, it's 0.135%. Why Gaussian distribution is important? We can actually prove this if you have random errors. If you have a huge number of random errors being accumulated, in the end, it's going to be a Gaussian distribution. So we're going to look at this so-called random walk model in the supporting information. The random walk model is this. You need to somehow imagine there's a drunk person, and this drunk person is going to move around. This drunk person is going to make a random decision about moving to his left or his right. And if he walks a very large number of steps, well, very likely his final position is different from his initial position. And let's say in each step he moves 1 meter. And then after moving 1,000,000 steps, what's the probability of finding this person 1,000,000 meters away from its original position, or 1,000 meters away from its original position, or 0 meters away from the initial position? So we can calculate the probability of finding that drunk person 1,000,000 steps away from the initial position, or 1,000 steps away from the initial position, or 0 steps away from his initial position. And then we can plot the probability versus the number of steps away from the initial position, and that will look almost exactly like the Gaussian distribution. It's not going to be the same because we are using a discrete model. So again, although the person will move 1,000,000 steps, still this 1,000,000 is countable. So we are using a discrete model to make approximation of the Gaussian distribution. So to prove this, we need to know this Stirling's approximation for the logarithm of n factorial. It adopts this form. To make it simpler, the logarithm of n factorial is roughly n times the logarithm of n minus n plus 1/2 times the logarithm of 2 pi n. So if this n is large, you typically can neglect all these terms. So we have this equation, and then we'll do this random walk model and assume that 50% chance the person is going to move to his left, 50% chance this person is going to move to his right. Of course, after 1 million steps, it is possible to find this person 1 million steps away from his initial position, but the probability is 0.5 to the power of 1 million to find this person 1 million steps to the left of its initial position, and also 0.5 to the power of 1 million to the right of his initial position. So these two probabilities are negligible. Now let's look at the derivation. So let's say this person made n steps, a total of n steps, and n is large enough, all right? And if the person's final position is x steps away from his initial position, and then he made m plus x over 2 forward steps and m minus x over 2 backward steps. So this is considered positive steps. This is considered negative steps. So the number of positive steps minus the number of negative steps is x. So this number minus this number is x. So overall, his position is x steps away from his initial position. And also, we can sum this two up. The sum of these two is the total number of steps n. All right. So now we're going to just look at the combinations of finding this person moving in the forward direction, this many steps, or the number of combinations of finding this person moving in the backward direction, this many steps. They are exactly the same. The expression is this. So again, this is the combination of selecting m plus x over 2 number of forward steps out of n steps. Now let's look at the probability of finding his position at x steps after a total number of n steps. Right? It's this. So on top, it's the combination. Okay, the number of combinations of finding the person moving in the forward direction, this many steps, and backward direction, this many steps. And over here, this is, 2 to the power of n. That's the, so this is 1 over 2 to the power of n. So actually, 1 over 2 to the power of n is 0.5 to the power of m plus x over 2 times 0.5 to the power of m minus x over 2. So for each individual step, you have 50% chance of moving forward and 50% chance of moving backward. So really, we just need to evaluate this, and in the end, I'm going to prove this is approximately a Gaussian distribution. First, we can see this probability distribution is normalized. So over here, you can pause the video and see if this is normalized. And now we evaluate the expression of the probability of finding that person x steps away from his original position. X can be positive, it can be negative. When x is positive, he is in the forward direction, and when x is negative, he is in the backward direction. So we can evaluate the logarithm of the probability of finding the person x steps away from its original position. It's this. All right? And then we just need to use this Stirling approximation to expand all those logarithm of factorials. So for example, the logarithm of n factorial is n times L1n minus n plus 1/2 times the logarithm of 2 pi n. So this is expanded into 3 terms. Similarly, this is expanded into 3 terms, 1, 2, 3. and this is expanded into 3 terms. 1, 2, 3. All right. 1, 2, 3. And then we have minus in ln2. We're going to do a lot of simplification. So, for example, this minus n minus negative n plus x over 2 minus n minus this negative n minus x over 2 is going to be 0. So this minus n, this minus n plus x over 2, this minus n minus x over 2, these 3 terms cancel, and then we have a simplified equation here. Well, it's still complicated, but we will further simplify this. So over here, we're going to just look at this term, this bottom 2. It's actually minus n plus x over 2 times ln 0.5. Over here, this is minus I think I highlighted the wrong 2, so this should be highlighted, and this should be black. So over here, focus on this, there's a minus sign here, so minus n minus x over 2 times the logarithm of 0.2. So if you combine this, you will get n plus x over 2 plus n minus x over 2 times ln2. All right, times ln2. That will cancel this negative n times ln2. So we further simplify the expression over here. And we keep simplifying this expression. So from here to here, I think all I did is I took this ln pi out. Okay, you get negative half ln pi here. You get negative half ln pi here. I put it here. And then we get this expression. So by looking at this pi here in the middle, and over here, this is you may view this as ln. So this one is equal to 1/2 times ln pi squared. So you can combine this and this. They do not completely cancel. And then you can do some other simplification. Now you'll get 1, 2, 3, 4 terms. And then we will make further approximations. If you have learned this approximation, this comes from the Maclaurin expansion or Taylor expansion of logarithm. So when x is much smaller than n, then the natural logarithm of m plus minus x can be expressed as this. So this is a truncated form of Maclaurin expansion. So we can put this back in here, So again, the Taylor expansion or Maclaurin expansion of the logarithm of 1 plus delta is simply delta minus 1/2 delta squared plus 1/3 delta squared. So if delta is 0.1, so you can verify the logarithm of 1.1 is simply 0.1 minus 1/2 times 0.01 plus 1/3 times 0.001 minus 1/4 times 0.0001. You can verify that with a calculator or with your computer. Delta can be negative as well. If delta is negative 0.1, you just replace every delta with negative 0.1. So when n is approaching infinity, we can further simplify this expression. And then after a couple more steps, so this is just algebra. In the end, we see the probability of finding the drunk person. X steps away from its original position is this. It's approximately the square root of 2 over pi n times e to the power of negative x squared over n. So this is Gaussian distribution when n is approaching infinity. Again, this uppercase n is the total number of steps this drunk person took. and this x is the distance between the final position and the initial position. Again, this x can be a negative number or a positive number. All right, so you get a distribution very close to Gaussian distribution. However, this formula is not normalized. It's not exactly normalized because if you try to sum up all those expressions, because x can be from negative n to positive n, if you sum it up, and you can make another approximation here. If you do that, in the end, the integral of this is going to be 1.414. It's not exactly 1. This is because in our derivation, I think I made several approximations. The Stirling approximation is one of them. And also, I think I made another approximation here. So this is another approximation. This is the truncated form of the Maclaurin or Taylor expansion here. So this is also an approximation. You can do this only when x is much smaller than n. But when we do this sum, you can see x is not necessarily much smaller than n. So again, we made so many approximations. That's why our result, although looks like a Gaussian distribution, but it's not exactly normalized. However, I want to say 1.5 is close enough to 1. So again, in summary, I just showed you if a drunk person move forward or backward with a 50-50 chance after a very large number of steps, for example 1 million steps, you will see the distance between his final position and initial position assumes the Boltzmann distribution approximately.